Alors, on va changer de sujet pour.
So we're going to change subjects for the second part of the afternoon. We're going to look at work that's being carried out in genetics. We'll begin with the seed. And for this first presentation, I'm going to call Mr. Simony. He's always present at the Herbalia meetings. 30 years of experience in R&D, principally in Switzerland. And he's going to talk to us about what's happening with seeds. So thank you for having come here. Thank you, Philippe. Thank you to the 𝗫𝗃𝗏𝗍 for having invited me and for allowing me to present a little study that we've been doing looking at the dormancy of seeds. This began with an informal meeting between 𝗫𝗃𝗏𝗍 and Bosco because there was no specific research finance in place for us. It's a small community, and this gave us the occasion to discuss, to debate, to chat with Agroscope and people from 𝗫𝗃𝗏𝗍, and it's always very enriching to do just that. We have shared issues, shared problems. We're working, for the most part, with the same species and the same branch, even though we're in Switzerland. So I wanted to talk about the results of a study that was carried out on seed dormancy. This is the result of a master's that was done by Stefano, who carried out his master, who produced his master's with us. And I went to the school in Bern, the agronomy college and school. But before beginning, 2 or 3 words. Agroscope, so what? That's the Federal Research Institute in Switzerland, a public institute for agronomy, which covers the main sectors of agriculture, animals right up to plants. It's for the French, it's like putting all the actor institutes under the same roof, roughly 800 people working together full-time on 3 principal sites and some secondary sites where I work in the Valley of the Rhône, in the southwest of Switzerland, near Val d'Aosta, and not very far from Chamonix. And so there you can really see we're able to look at climate very particularly, and we've got linguistic diversity, etc. So the studies really have to take everything into consideration. So this is applied research in order to talk about production and study the phenomena of production. So if you look at the title, the response of dormant seeds in the maps to the karrikinolides, KAR1, which are smoke-derived. So seeds, well, it's very important. It's central to what we're doing and for agricultural production in general. Most of the crops come from the seeds, and this is where research begins. The genetics, it's very important for us. For institutes, it's important. And often in Agroscope, we have to write on the new species, the domestication of new species, alpine species. We have small SMEs and startups who want to work on this. It's very schematic. What do we have? We've got this embryo with nutritional tissue, and then you've got light, water, temperature, oxygen, gas exchanges, particularly oxygen. That's going to get things moving. It's going to get the organism moving. So you can be in this is how it goes from almost dying to life. These are the ideal conditions. There are 2 classes of dormancy. You've got the tegumentary, you've got mechanic resistance. This is a tegument which is waterproof. And then you have your mechanical resistance. That's fairly self-explanatory. And also, leguminous and all the leguminous vegetables are quite well known for having this kind of seeds. It's usually fairly simple. Often we don't realize, because when we have the combine harvesters that come in and harvest these, well, they can be brought in by the combine harvester. You're going to see that you're going to have the seeds marked by the mechanical action. Some species have to be protected, allow them to grow and develop at the adequate moment. But that's not what's of interest to here. No, we're looking at embryonic dormancy, I believe. The internal problems, the internal dormancy in the embryo, the seed, is harvested at an optimal mature stage. But all the external factors have to be in the seed. The embryo needs specific connections in order to start germination. And there could be problems of presence of light, or the quality of the light could be different, the different waves of darkness, shade. There could be exposure to dry temperatures, ambient temperatures, but in dry conditions in certain time in order to terminate maturity. There can be certain demands for exposure to certain temperatures. When the seed is humid, you could also talk about what else, questions of pyrolysis, or this going through fire. We're going to touch on it, but that's not really the angle through which we want to look at it, because that's simply going to destroy the tegumentary element. It could be a thermal shock, a heat shock, which will destroy the seed. When we did a steam treatment on mallow, we saw that. We have to look at the temperatures. If you 70 degrees, between 60 to 70 degrees, you put it in for a certain number of seconds, and these are very short treatments. We saw with mallow, we saw germination which improved, and this was a thermal shock which actually killed the seed, although I am certainly getting off target here. Right, so what do we do then? What are we looking at? We're looking at the embryo. Is the embryo generated and germinated? That's really the question. It's a question for a physiologist. So all of this is what? It's very complex. There are lots of publications out there on germination or other specificities for some species or some botanical families. But to keep things simple, let's say the synapse, psychic synapse, the acid, this kind of ABA, and you have an accelerator, so you're going to find this balance between putting on the brakes or accelerating, which is going to allow the seed to remain in dormancy, or whether it's going to be germinated. Now, of course, there are different variables which are intraspecific inside the same species. You can see a division between different varieties. You can have dormancy, which changes at the crop when the crop rises. There are also other areas that we don't know particularly well, that even year after year, even the seed is mature, you're going to have dormancy, which is going to be very different, germination, which is going to be very different. Temperature, this registered from the mother plant, or the level of nitrogen or water stress, or the quantity of ABA, which has touched the embryo or the seed. You're going to see that's where the hindrances are going to come in with regards dormancy. So, this problem then with embryonic dormancy, well, how do we release the handbrake and how do we push on the accelerator? Well, rather you go through stratification, and by that I mean going through cold for a certain amount of time. For some seeds, this takes time. The multiplicators do this in these seed plates which they put into the fridge, so you have to anticipate that. Or you can do this in a lab. You can use pyruvic acid, because this allows us to speed things up and encourage germination. In Switzerland, almost all of production is done in an organic way. So when you've got ABA and CA, you're talking about synthetic acid, and this can complicate things. I don't know how it's used in France. I really am not sure what the legislation is. The problem is for us, can we find alternatives for stratification? Something that is quicker, easier to implement, not expensive, and easy. So that's what we're looking at just now with GA3. And then there was a study, a bibliographical study, which was carried out by 𝗫𝗃𝗵𝗿 and Agroscope. We pooled our data and we carried out research on different species in the maps. Very few publications are out there on this subject, so we widened this to include other species, especially trying to identify different techniques that could be used to resolve this problem linked to dormancy. So there are two in front of you. You have dormancy, and I've just explained that very schematically. We also talk about priming. This is another approach. Sometimes you can get confused by the two. Priming with the opiates, with fennel or with carrots. We are talking about long period of time, and so what we have to do is give an initial propulsion to the seed to get it going. Make sure that this is considerably encouraged for germination, and then we dry it, and then the farmer can seed his field. But this first impulsion has to be given to include rapid germination, and quite a compact germination at that. That's priming. So in the bibliographical research, we were looking for certain elements and the different opportunities. We really picked up three groups: fumigation, even if initially that didn't seem very simple to us. For, any kind of seed covered in mulch or straw or any kind of fertilizer. It's not the most it's not the easiest to put into place. Now we've got the homopriming, I talked about that, and we also had the opportunity with a local partner to test plasma cold. It's ionized gas at low temperatures produced by an electric charge through a gas. There is some literature out there looking at decontamination of seeds as well, and that's all done through testing. So all of that to say the following: we've got this species, you've got Alchemilla, you've got Lavandula, Rhodiola rosea, Verbena officinalis, Veronica officinalis. These are the 5 ones that were retained for the study, particularly lavender, with all the different seeds, different botanical families, different sizes. And the technical area, we did a pre-screening. The questions of, the amount of time that the seed is exposed, the dosage. We didn't want to carry out, you didn't want to duplicate things, so we took the time to do this at the beginning. With homopriming, we tested plasma froid, smoke water, different smoke for water. This is, I think it's better to say it in English than in French because it really is that. This is a component, KAR1. I'll give you more information on that afterwards. And then a control, negative control, and a positive control with GA3. There were roughly 200 treatments if you add them all up together, the different species, the different doses and exposure time. You've got 198. And what came out of all this? Well, the positive signs, because there was no repetition in this, it was a one-shot game, were very prudent. What came out was that the treatments by smoke water and KAR1, everything that was different, and plasma, wasn't that interesting, but the second part, the smoke water and the KAR1 was. And in the second part, we remain very much focused on smoke water and KAR1 because, well, they seem to work. This smoke water, then, what is it? It's water. It's water derived from smoke. So when there's, for example, when there's a forest fire, There's a great deal of smoke, there's a great deal of ash, it falls down, and then you have this seeds or species that were never there can be found after the fire has been put out. So we're not talking about the action of the fire, the mechanic action. It can be tegumentary detrimental or any kind of thermal shock, but you have some chemically induced seed germination. You do see that this is a result of cellulose, pyrolysis, particularly with cellulosis. And what falls back down after a fire in the form of ash back into the ground, and then you have, well, that's interesting, and then you have rain, which rains upon this. It's like it creates a kind of infusion, and these components which are going to induce seed germination, they're going to push on the accelerator in terms of germination. These are species that can remain in the soil for years in spite of wet episodes. They're grains that are seeds that are going to germinate after these forest fires, bizarrely enough. So there's quite a few of them. It's not something that we've really been looking into, and I'd never really heard about this with regards MAPS, and that's why it's so interesting to work on it. But I did look at the different components of the various karrikines. You can see there are analogues which have a positive effect on germination. You have other components which belong to the cyanohydrins. They're not quite so friendly, not quite so kind, but they can have a positive effect on germination of some species. Nothing's ever perfect though, because there are other components that are going to be present in this situation when you have these forest fires, that is. You have cellulosis pyrolysis. You have what we would call antagonists who are going to hinder germination. So you have to find a balance. There is a balance between the different components.
So setting fire to promote germination, burning components, is something that has been known since the 70s. But more accurate knowledge has been developed to explain how these components could start this promotion. It's been studied in Australia and in South Africa. It makes sense given the forest fires and bushfires that they had there. There's a lot of discussion going on in terms of receptors. Analogies are made with other chemical mediators that are being studied, but it's still ongoing, and there's still a lot to focus on and to learn about it. So, what did we do for this study? What did we do with the smoke water? We did it very DIY-like. We took a bee smoker. We produced a lot of water. We ionized water, and then we put the smoke in bottles to really so that the water would trap the components from the combustion, and then the water becomes. It looks maybe like a pea sample, urine sample, but it's the water that captured the elements. Then we had different dilutions level, 1/1000th, 1/10th, etc. And given the literature, there was another component with the positive action. It's KAR1. So we bought it. It's a chemical compound. And then we did a mother solution. With molar dissolution. And then we had several dilutions, 5 different dilution levels. Dilution levels. And for fun, the students also looked at food-based products that you can add when making sauces to bring the smoky flavors. And so you have liquid smoke. And so we mixed 50-50 those two types, and we also made the different dilution levels. Our tests were carried out in Petri dishes. Another impact on our results is that we could have dipped the plants in the solutions, but to make it easier, we used we intake paper that took in the liquid. We had days at 16 hours with 8 hours night at 18 degrees. It's a day-night cycle that we usually use. And so with the blotting papers, we stopped when the radicals were twice the length of the seed. The results now. First result on the Alchemilla. When I talked about intraspecies variability, that can explain the mother plant or the graft plant, we had to exclude some because we had to exclude some plants because they actually germinated too well. And Alchemilla actually was borderline. It was a first study. There is a lot of perspective to take it further. But our weakness was that apart from Lavandula, we had 2 varieties furnished or provided by the 𝗫𝗃𝗏, and for the other studies, we only had 1 batch and 1 variety. We only had 1 for Alchemilla. So in water, the germination was about 60%. With GA3, we had an improvement to 80%. But germination levels were pretty high anyway, so the results were not interesting to use. With KAR1, the concentration of the germination is close to simple water, smoke water, same thing. Food grade liquid smoke, same thing. So the results were not interesting for Alchemilla. Second species, we used the Carla variety for the lavender. It was a pretty old batch of seeds, so in water we had an under 20% rate. But with KAR1, we pushed the germination level compared with the water control group, 13.5% for the water control group. With KAR1, we took it up to 30%. So it's still lower than GA3, that was 50%. And with smoke water for 1:1, we had no results. For the Rapido variety, we have a higher result because with GA3 we're not at 50 but at 67% this time. The concentration levels of KAR1, with higher levels of KAR1, we had a growing response. The more KAR1 we had, we reached the same level as GA3, so it was very interesting. We were very pleased with this result. But with smoke water containing this component as well, we didn't have any response. Back to the Rapido example, the difference compared with the previous graph is that here the red dots that you could see means that we analyzed the KAR1 within the smoke water. It's the molar concentration on the top. And so the red dots show that even with smoke water at low dilution, we still have a very strong, low concentration of KAR1. So some of the lowest levels for pure KAR1 levels. What we can see in the 5 species is that non-diluted smoke water inhibited the germination fully. so total inhibition of germination. With Rhodiola rosea, which is typical from the Alps, it's also a dormant seed. It doesn't germinate a lot. In water, it's 14.5%. It's 50% with GA3. After 1 month and 1 degree, we reached the same level of GA3. But it takes 6 weeks. For Rhodiola, we had 0 response with the pure component and smoke water. Verbena is something that doesn't germinate very well. But here with the water that the batch we used actually germinated very well. Was it a more mature batch? We don't know. We couldn't prove anything because the control batch germinated very well, which is not the usual case for Verbena. And last species, Veronica officinalis. It's also very interesting because unlike lavender that reacted very well to the pure component and no reaction to the smoke water, with the Veronica we have a very good response both to the pure component KAR1, to smoke water at 1/10 that are close to 100%, close to even higher than the GA3. Whereas we only have 50% with water. So it reacted very well to the food water component, food grade component, highly diluted. But smoke water without dilution was once again inhibiting germination. So once again, this is a different graph to show the KAR1 concentration in the smoke water and in the pure solution with KAR1 only. Unlike lavender, which had an increased germination level in parallel with the KAR1 concentration, here the concentration, the sensitivity of response is very different. It starts much lower with the KAR1 concentration. To conclude, we got very interesting signals and results. I had never heard of these smoke water or such components used to lift dormancy in maps. We could see that the responses were very variable depending on the species. In Alchemilla and Rhodiola, no response. Lavender, very good response to KAR1, but no response to smoke water. There are many questions raised. Veronica had positive response to both, but with lavender, we had positive response with increased concentration, whereas Veronica had positive response to lower concentrations. And smoke water, non-diluted, can have an inhibiting effect on every species. But when there's a difference between no dilution and 1/10 dilution, this is a space where it would be very interesting to deepen the studies. Maybe sensitivity is about the KAR1 concentration, or it can be other inhibiting substances in the smoke water that actually stop germination. And for smoke water, our concentration levels, even with low dilution, the levels of KAR1 were very low. Also, the duration of exposure was pretty long. The GA3 treatment for Rhodiola is 8 hours. Then you take it out, you rinse it. But we used blotting paper to ease our testing, and so the paper was filled with the solution during the test, so it changes the duration of exposure. Also, the temperature of germination can have an impact. Maybe it would change the responses if we changed the temperature. We have interesting results that could motivate further research. We need to have more sessions and varieties per species. For instance, Lavandula angustifolia showed no response to smoke water, but smoke water from another burned plant actually had better effects in another study. So maybe the components, the balancing components in the smoke water actually would change the response of the plant species. So we would like to have more species to compare the results. Looking at the literature, maybe we can produce smoke water by crushing coal, wood coal. It would be easier than our DIY method to create smoke water. And including other karrikinolide, like KAR1, which can be found in chemicals retail providers. So we could include KAR1 in our experiments. We could also boost our own smoke water with both components to see how it reacts, if it increases the inhibiting effect or not. And we could change the exposure duration of bloating paper. It would be another factor to study. So there's a lot to look into with this topic. Thank you, Xavier. Round of applause, yes, thank you. There's an article being reviewed, actually, on the topic. We have a couple of minutes to answer questions. Short questions, short answers, please.
Merci beaucoup pour la présentation.
Thank you for your presentation. I think I missed something important in your protocol. In the initial protocol, to shift to in vitro testing, how did you deduce that it was KAR1 that induced embryo germination and maybe not a combination like, as you said, other karrikin compounds? Was it the concentration of smoke? Was there a specific methodology to deduce this? There are many publications, not on maps, but on other species. So we started from those studies. This was the first component studied. There are many articles on the positive impact of KAR1. But it's very interesting what you're saying. There are other karrikinolide components. Will they have an effect or not? Maybe the concentration is not the only issue. So the investigation field is vast. There are other inhibitors that can actually have an impact on the effect of the karrikinolide. The impact of the ashes, maybe the combustion can have an impact on very different chemical profiles of these compounds.